Video, we're going to be talking about titrations and pH curves. If you've ever taken a chemistry class, you probably came across a titration at some point in time. And so in this video, we're going to be talking about titrations and how we go about calculating pH of solutions based off of different types of titrations. Now, this is going to be part one of a series of videos that I produce in relation to just titration specifically. And so as we talk about titrations, the first question you have to ask is, what is a titration? Now, the answer to that question is titrations are when you take a known solution and that's used to titrate an unknown solution to determine its concentration. This usually is achieved by performing a neutralization reaction between an acid and a base. Oftentimes, when you have the setup for a titration, you have the burette that's in the lab, and then the burette is controlled, and what's inside of the burette is the titrant, and the titrant is a known concentration. And so below it you have an Erlenmeyer flask, and in the Erlenmeyer flask is an unknown sample of whatever. So this is your unknown. So we're going to add in a specific amount of the titrant into this solution, and so over time what we're going to do is we're going to measure the pH versus the volume of titrant added. And so in order to do this, we have to know a few things. We have to know what the titrant is, we have to know its concentration, and we also have to know how much of the titrant we added into the unknown. But the unknown, we have to know how much volume. So the question is, what volume of the unknown solution do we have in there? And so now there are different types of titrations, and so that's why we're going to make this a little bit different video. We're going to make it into a series of videos. And so what we're going to focus on today is we're going to focus on a strong acid and a strong base titration. And we're going to look at how the pH changes over time, and we're going to not necessarily graph it, but we're going to kind of study what happens to the pH as the volume of titrant is added into the flask. And so now the example that we're going to focus with and we're going to work on is we're going to take a solution where we have 50 milliliters. So this is our example here. So we're going to have a 50 milliliter sample of 0.2 molar nitric acid solution. And to this nitric acid solution, we are going to add a specific amount of sodium hydroxide. It'll be titrated with 0.1 molar NaOH. So nitric acid is a strong acid and sodium hydroxide is a strong base. Now before we do anything, we're going to calculate the initial pH of the solution. And so we don't really need anything other than just the molarity of the nitric acid. Now, nitric acid being a strong acid, the concentration of the hydrogen ions is equal to the concentration of the nitric acid because it being a strong acid. So to calculate the pH of this, we're just going to take the negative log of 0.2, and what we end up with is 0.699. So that's just the initial pH of the solution. Now what will happen if we add in 10 milliliters of 0.1 molar NaOH? So to do this problem here, there's a couple things we have to take consideration. All right, the first thing here is we need to look at the stoichiometry. We need to apply some stoichiometry. And the second thing is that we'll calculate pH after we determine what's left over from the solution. So in order to do the stoichiometry, we're going to write out the equation for nitric acid reacting with sodium hydroxide to form sodium nitrate and water. Now we're going to figure out our initial, and then we're going to figure out the change, and then we're going to figure out after. This is not the ice chart. This is different from the ice chart. It's just the stoichiometry specifically. So we need to figure out how much of the nitric acid is left over after the titration. So we have 50 mils of the nitric acid, and we're going to do 50 times 0.2. So we get 10 millimoles of HNO3. So just so you know, I take the 50 milliliters and I multiply it by 0.2 molar, and that's what gives me 10 millimoles. And we're going to do that for each case. So we did it for the nitric acid. We're also going to do it for the sodium hydroxide. So we're going to take 10 mils of the sodium hydroxide, and we're going to multiply that by 0.1 molar sodium hydroxide, and that will give you 1 millimole. So we have 1 millimole of sodium hydroxide. So you can see that sodium hydroxide is a lesser amount. So we're going to subtract from 1 here, subtract from 1, and that leaves me with 9 millimoles of the nitric acid. So we could add the other side, but it's not necessary because we know that nitric acid is a strong acid and the pH is dependent on its concentration. So we're going to figure out the concentration of nitric acid. So we're going to take the 9 millimoles and we're going to divide it by the total volume, which was 50 plus 10, so that's 9 divided by 60 milliliters here. So 9 divided by 60 gives me a concentration of 0.15 molar. Now, since we know that nitric acid is a strong acid, so we're just going to calculate the pH equal to negative log of 0.15. And that gives me a value of 0.824. So you can see that the pH does not change very much from the initial pH, which is 0.699, to this new pH of 0.824. So this example that we just did here represents a typical titration problem where we just have to take the information given to you. In this case, we have 10 mils of a 0.1 molar solution added into the 0.2 molar solution of nitric acid. Now, another problem would be where if we were to add in 100 mils of 0.1 molar it's sodium hydroxide. So now we're going to do a separate problem. So it's a new one, but this time we're adding in quite a bit more. So we started off with 0, went to 10. Now we're going to do 100, and let's see what happens here. So before we do anything, so the first thing is the stoichiometry. So you have nitric acid reacting with sodium hydroxide to form the NaNO3 plus H2O. Now these two are not important at this moment, but when we start working with weak acids, it's definitely going to be something that isn't important we have to pay attention to. So initially the change, and then after the change, so how much is left over. So we have 10 millimoles of the HNO3. We're going to do 100 times 0.1 for the sodium hydroxide, and that also gives us 10 millimoles. So you can see we're at a point where now we have equal moles of acid and base. If you know anything or remember anything from previous classes, we are at what is called the equivalence point. The equivalence point is where the moles of acid are equal to the moles of base. So we're essentially neutralizing all the acid in the solution. Now, what's unique about this is that since we're dealing with a strong acid and strong base, what we see happening here is they neutralize each other, and so the resulting pH is 7, because that's the halfway point. And since they're both strong acid, strong base, they neutralize in the midpoint, which is 7. Okay, so in this problem, we are going to work a new problem, and we are going to be adding in 200 milliliters of 0.1 molar sodium hydroxide to a 0.2 molar HNO3 solution, and that is 50 mils. So it's like before, we are going to be working two different parts. The first part is going to be the stoichiometry part, and to do that, we are going to first write out the reaction, and then we will figure out how many millimoles of both reactants we have present. Now, for the nitric acid here, we have 50, so that's going to be 10 millimoles. Remember, the way I'm getting this, I'm doing 50 milliliters times 0.2 molar, and that gives you millimoles. Now, we're going to do 200 milliliters of sodium hydroxide multiplied by 0.1, and that gives me 20 millimoles of sodium hydroxide. Now, we can see this is different from the previous problem. All right, so what we're going to do is we're going to subtract 10, because the nitric acid has lesser amount of millimoles, and so we're going to subtract from 10 here. That leaves you with 0 millimoles of HNO3, but it leaves you with 10 millimoles of sodium hydroxide. Now, so since we have excess sodium hydroxide left over, the pH is going to be dependent on how much sodium hydroxide is left over. So we're going to figure out the molarity of the sodium hydroxide, and we're going to take the 10 millimoles and we're going to divide that by 250 milliliters, and what we end up with is a 0.040 molar solution of sodium hydroxide. So to calculate the pH of this solution, we first have to figure out the pOH because of the hydroxide ion, and that's just simply taking the negative log of the 0.04 molar, and that gives me 1.39 for the pOH. To solve for the pH, we're going to do 14 minus the pOH. So 14 minus the 1.39, and that gives me 12.61 for the pH of the solution. And that's what we should expect because there is excess sodium hydroxide left over. So as I was talking about the pH of the solution here, we went through a series of titrations, and the initial pH of our solution was 0.699. Then after we added in 10 mils of sodium hydroxide, it went to 0.82. Then after we added in 100 mils, it went to 7. Now at 200 milliliters, we see it at 12.61. Now these are just staggered amounts of sodium hydroxide put in it. If we were to actually go through and calculate the pH at like half a mil every time we added in a half mil of sodium hydroxide, what we would end up with is a pH curve. And so a pH curve basically is where you can get an idea of what's going on in the solution as you add in the sodium hydroxide. So in this case here we have volume of NaOH as we add in, and this increases here. So what we would see is a curve that looks something, let me draw better, that looks something like this here. And so for a strong acid, strong base titration, your equivalence point is right in the middle of this curve, and it's going to occur at 7.0, and that goes for any strong acid, strong base titrations. Now, where things get to be different is where you have a weak acid, strong base titration, or you have a strong acid, weak base titration. So in the next part of this video, we are going to be talking about the weak acid, strong base titration. And in the third video, we're going to talk about strong acid and weak base. So keep your eyes out for the next part 2 and part 3 of videos pertaining to titrations. All right, thanks.